There are a lot of parallels between the daunting prospect of IUPAC nomenclature and learning how to swim. For someone first learning to swim, there are a lot of steps and things you need to do in just the right order to be good at swimming. The same is true for IUPAC nomenclature with its rules and subrules and sub-subrules. This video is a bit like reading a textbook on how to swim. No one expects you to read a textbook on how to swim and then immediately jump into a swimming pool. Once we learn these rules, you'll need to do lots of repetitive examples that will help solidify the rules and build an intuition about naming. This video is heavy, but I predict it'll be the reference video that you bookmark and keep returning to throughout the rest of the semester. Hey there, ninjas. In this video, we are going to lay out all the rules for IUPAC nomenclature. Every major rule, every subrule, every sub-subrule, and every tiebreaker you're going to need for any molecule this semester. Let me be very clear about one thing right up front. This is not how you learn nomenclature. This is how you organize it. Think of this as your reference guide for all of the rules. The video you keep coming back to and watching over again as things start to feel confusing or arbitrary later on. I went over the basics of IUPAC nomenclature in a different video, and perhaps pause this video and watch that one before coming back. But every IUPAC name can be broken down into 5 parts: the stereochemistry, the substituents, the parent, the unsaturation, and the priority functional group. Not every molecule will have stereochemistry or substituents, but every IUPAC name will have a parent syllable, an unsaturation syllable, and a priority functional group syllable. And the order never changes. I'm going to walk you through a step-by-step guide that makes the rules actually make sense. And step 1 is always the same. Find the longest chain of consecutive carbon atoms, including the priority functional group. Priority matters. Molecules may contain more than one functional group, but only one functional group gets to be the priority functional group that defines the end of the name. All the other groups on the molecule become a substituent. That means we need to know the prioritization of all of the functional groups in organic chemistry. This is by no means an exhaustive list, but this list contains the most common functional groups you're likely to see in a molecule that you might have to name in this course. This is a priority list in order. The carboxylic acid is the #1 priority functional group. Of the functional groups we're likely to see in this course, the carboxylic acid is the highest priority. Other functional groups work their way down this priority list, and at the bottom are a set of free functional groups. The ether, the halogen, and the alkyl substituents are not priority functional groups. They don't dictate the suffix on the end of the IUPAC name. They are little bits of free decoration that we can put around the molecule that don't have priority. You're going to need to know this list. Molecules can be simple, molecules can be very complex, but step number 1 for IUPAC nomenclature is to find the longest consecutive carbon chain that contains the highest priority functional group, with the caveat that it does not necessarily have to be horizontally linear across the page. The longest consecutive chain may curve and loop around, but it's the longest consecutive chain of carbon atoms that contains the highest priority functional group in this list. If there happens to be more than one chain with the largest number of carbon atoms containing the priority functional group, we break that tie by prioritizing the number of substituents. We choose the longest consecutive chain with the most number of branching points. Like I said earlier, you can't read a textbook on how to swim and then go jump in a pool. This video will be a good reference later on in the semester. So to ground these rules for this video, we're going to follow this molecule along to its IUPAC name. For this molecule, for step number 1, we want to find the longest consecutive carbon chain containing the highest priority functional group. In this molecule, on this list, the aldehyde would be the highest priority functional group in this molecule. One choice would be these 3 carbons containing the aldehyde. This would ultimately not be the best choice because it's not the longest consecutive carbon chain containing the priority functional group. Another choice I see is this branch of 7 carbons containing the alkene. This would not be the right one because the aldehyde is the priority functional group, and this chain does not contain the aldehyde. The linear backbone running horizontally along this molecule contains 7 carbons and the aldehyde. This is a good contender for our longest consecutive carbon chain. However, this chain only has 2 branching points along the entire molecule. This carbon chain, however, also contains 7 carbons in its longest consecutive carbon chain, also contains the aldehyde, and now has 3 branching points along its backbone. Following the rules of step 1, this is our longest consecutive carbon chain. This carbon chain defines the parent hydrocarbon from which this molecule will be named as a derivative. Step number 2, after we found the parent hydrocarbon, is to number the carbons in that chain. This step has lots of rules and subrules and sub-subrules and tiebreakers. So before we get back to naming our molecule, let me show you a couple of other examples to exemplify some of these rules. When we number the parent hydrocarbon, we always can number one of 2 directions, and we want to number to give the highest priority functional group the lowest possible number. In this molecule, the amine is the priority functional group. We could number left to right or right to left. Step number 2 says we number number to give the highest priority functional group the lowest possible number. For this molecule, we would number right to left so that the amine can sit at carbon number 2, rather than numbering left to right, which might make more sense but puts the amine at carbon number 6. 2 is a lower number than 6. For this molecule, going back to our previous list, the alcohol is a high priority functional group and the halogen is one of our free functional groups that does not have a priority. To give the alcohol the lowest possible number, we again number right to left, put the alcohol at carbon number 2 rather than at carbon number 3 had we numbered left to right. Notice that by doing so, we give the halogen carbon number 4. And that's okay because we're giving the alcohol the highest priority group the lowest possible number. It might make more sense to put the chlorine at number 1 and the alcohol at number 3, but that wouldn't follow step 2. If there's more than one instance of the high priority functional group, we number to give the first instance of that group the lowest possible number. We number this left to right to give the alcohols carbon number 1 and carbon number 3, rather than right to left, which would put the alcohols at 3 and 5. If there's more than one instance of the high priority functional group, and numbering from either direction puts that high priority functional group at the same position, then we ignore the priority functional groups, we start back over at the ends, and we count to find the lesser priority functional group and give it the lowest possible number. Here, numbering from each direction will put the alcohol at carbon number 2. We ignore the alcohols and we look for the first lower priority functional group, the bromine. Numbering from the right would put the bromine at carbon number 3, which would be better than numbering from the left, putting the bromine at carbon number 4. If we work our way in from the end, and the position of the first non-priority functional group is the same from both sides, if those tie, then we keep moving into the position of the second non-priority functional group, and we give it the lowest possible number. If those tie, we move in further to the third non-priority functional group, and we keep moving inward until we find one point of differentiation that allows us to choose a direction for numbering. If, however, we go all the way through the molecule and they're really the same numbering both directions, here the amine groups both tie at carbon number 2, and the lower priority functional groups both tie at carbon number 3. Then we compare the first groups from each end, and we give the alphabetically first group the lowest possible number. Here, the first groups from each end are both amines, they're both the same, they both tie, so we go to the second group, and bromine is alphabetically first before chlorine. So we ultimately number this molecule left to right. Had those tie, we would have gone to the third group in and number it alphabetically until we found a point of differentiation. But friends, if we get to the end of the analysis and it's really the same both directions, we can't find a priority difference, we can't find an alphabetical difference, then the molecule really is just the same left and right. I call these types of molecules palindromic molecules. And for a truly palindromic molecule, it doesn't matter if you number it right to left or the left to right. They're pancake flips of each other and it'll be the same either way. Finally, for cyclic molecules, we give the highest priority functional group carbon number 1, and we number around the ring to give the lowest overall set of numbers. Here, the alcohol is highest priority, so it gets carbon number 1 by default. Numbering clockwise around the ring gives us substituents at carbons 1, 2, and 4. Had we numbered counterclockwise, the substituents would have been at 1, 3, and 5. And the set 1, 2, and 4 is a lower overall set than 1, 3, and 5. For our molecule then, our 7-carbon chain, we'll number this one right to left. The aldehyde is the highest priority functional group, and we'll give it the lowest overall possible number. This one was straightforward to number using step 2. We didn't have to go to any of our subrules. Once we've found the longest consecutive carbon chain, and once we've numbered it based on its priority functional group, step 3 is to name the parent hydrocarbon. Every organic molecule is named as a derivative of some parent hydrocarbon. So we need to name that parent hydrocarbon so we can derivatize the rest of the name based on the rest of the substituents. To do that, you need to know the names of the small hydrocarbons. In that previous video, we looked at the first 12 hydrocarbons. You need to know the name of those first 12 hydrocarbons. After 12, the name is systematic up to 19, and beyond that, we don't really need to worry about it. Once we have named the parent for our longest consecutive carbon chain, we update the name of that parent to account for any unsaturation or any priority functional groups if they're present in the molecule. Our molecule has 7 carbons in its longest consecutive chain that contains the priority functional group. So we start from the base parent hydrocarbon heptane, hept being the word for 7. But this molecule isn't going to be a heptane because we have both unsaturation and a priority functional group. To account for the unsaturation in the name, we update heptane to heptene, the ENE being the syllable for a double bond. I have an entire separate video on all the naming rules for alkanes, alkenes, and alkynes, and I'll put that link in the description below. But this molecule is also not going to be a heptene because we have a priority functional group in this molecule. Going back to that table at the beginning of this video, the aldehyde as a suffix has Al as its syllable. So this molecule is not going to be a heptane, it's not going to be a heptene, it's going to be a heptene-al. Each syllable is very important, each syllable is very descriptive, and it's important to pronounce each syllable correctly. Heptene ene, al. That's very different from hept and al. So we want to be very careful with our vowel sounds when we're pronouncing these names. Now we have 3/5 of the name already complete. We're ready to identify the substituents and their location. Small hydrocarbon-based substituents are so ubiquitous we have special names for most of them, and you need to know this table. Each box shows a different hydrocarbon substituent, with Mr. Squiggles being the attachment point to the parent hydrocarbon. So if we have a parent hydrocarbon with a 1-carbon substituent hanging off of it, that 1 carbon we call a methyl substituent, and sometimes we abbreviate it ME. METH, meth, is our syllable that means 1 carbon, and YL is a syllable that means that it's attached to a parent hydrocarbon. It itself is not the parent. Ethyl, eth is our syllable for 2 carbons, and YL means that 2-carbon chain is attached as a substituent on a longer parent hydrocarbon. What's interesting is there's only one way to have a 1 or a 2-carbon substituent, but 2 ways to have a 3-carbon substituent. We could have all 3 carbons in a row. That would be N-propyl, where N stands for normal. Or we can have a substituent that's kind of got this forked tongue at the end. A different arrangement of those 3 carbons, it's an isomer of those 3 carbons, and so we call that isopropyl, an isomer of the 3-carbon substituent, isopropyl. There are 4 ways to have a 4-carbon hydrocarbon substituent. The straight chain 4 carbons is the normal way, that's N-butyl. When we still have that straight 4-carbon chain, but it's attached at the secondary carbon rather than the primary carbon, we call that the sec-butyl. Notice there's one with the forked tongue, an isomer of that 4-carbon chain, that's the isobutyl group. And when we have one central carbon with 3 sprouting methyl groups, that is the T-butyl group. You need to be comfortable with this list. Pay close attention to the 4-carbon substituents. The syllables we use for other substituents and molecules you can find back on that original table at the beginning of this video. On carbon number 1, we have the aldehyde. That is the priority functional group, so we'll find the syllable for the aldehyde corresponding to the priority functional group. On carbon number 1, we have an al substituent. On carbon number 2, we have a 1-carbon substituent. That would be a methyl group. But notice something interesting. On carbon number 6, there's another methyl group. At 2 different positions in this molecule, we have a hydrocarbon substituent with 1 carbon in that chain. This happens all the time. If there are multiple identical substituents, we use a numerical modifier like di or tri or tetra. So for this molecule, we have a methyl group at carbon 2 and a methyl group at carbon 6. We would write this as 2,6 dimethyl. We need both location numbers to tell the reader where those 2 methyl groups are. And we need the di syllable to tell the reader that there are, in fact, 2 methyl groups. We would even include 2 numbers if both methyl groups happen to be sprouting off of the same carbon. If both methyl substituents happen to be on carbon 2, we would name this as 2,2 dimethyl. We would keep both numbers and the dimethyl as the name of the substituent. Continuing on, using that table that we had before, on carbon number 4, we have an alkene, that is an ene group. And on carbon number 5, we have a 2-carbon substituent, that is the ethyl group. This is the list of all the substituents in this molecule. This is the list of how our parent hydrocarbon is derivatized to form the name of our molecule. We don't have a benzene ring in this example, but if we had a benzene ring as a substituent in the molecule, we would name it as a phenyl group. And the big subrule in this category is sometimes substituents are complicated and have branching and other substituents of their own. Naming molecules with complex substituents is probably the most complicated aspect of the IUPAC system at this level. I'll go through the rules here for our reference video. In a future video, we'll go through some worked examples that have complex substituents. To name a complex substituent on a parent hydrocarbon, first we number the carbons in the longest consecutive chain in the complex substituent, starting with number 1 at the attachment point to the parent hydrocarbon. Then we name the whole complex substituent as a little mini molecule, except instead of the priority functional group syllable at the end of the name, we put YL because it's going to be a substituent on a longer parent hydrocarbon. And we wrap that entire name of that mini molecule up in parentheses, and we use it as an entire substituent name. Once we're done finding the substituents, we're finally ready to start constructing the name. We've done the hard work, now we're racing across the finish line. To put all this together into an official IUPAC name, we start by listing all the substituents on the molecule in alphabetical order in front of the parent name. And of course, there are some subrules and subrules for alphabetization. We do alphabetize by the I in isosubstituents or the C in cyclosubstituents, but we do not alphabetize by the N in normal substituents, S in sex substituents, or T in tert substituents. Nor do we alphabetize by the numeric modifiers di, tri, tetra, etc. So for this molecule, the AL and the ENE are taken care of in the name of our parent hydrocarbon. So we're alphabetizing dimethyl versus ethyl. And be very careful here. We're alphabetizing by the E in ethyl versus the M in dimethyl, not the D. We do not alphabetize by numeric modifiers. And E comes before M. If we had a complex substituent, we would alphabetize the complex substituent by the first letter regardless of what it is. And finally, when we're putting together the name, we separate numbers from numbers with commas and numbers from letters with dashes. So putting it all together for this molecule, at the 5 position we have the ethyl group. We separate the number from the letter with a dash, then another dash, and 2,6 dimethyl. After that, we run right into the parent hydrocarbon. We have two letters here. We don't separate letters from letters with anything, so it runs together as one word. After the hept, we need to know the position of the alkene, so we interrupt the name with the 4 as the position of the alkene. In the official IUPAC rules, the number always immediately precedes the syllable it is modifying. The 4 is telling us where the "een" is, so the 4 needs to come directly before the "een" syllable. In an old version of the rules, it was acceptable to move that 4 elsewhere in the name. I'm not going to go over that. We're just going to go with the most updated rules. We end with our syllable for the aldehyde. Typically, we would also need the numerical location number for the priority functional group to let us know where it is in the chain. But an aldehyde with the hydrogen at the end has to be carbon number 1 by definition. And when it has to be carbon number 1 by definition, there are a couple of functional groups like that, it's acceptable to omit the 1 and leave it off the name. Finally, we glance back through the molecule one last time, and we assign stereochemistry labels to every chiral center and every alkene in the molecule. This isn't a video on how to assign stereochemistry labels. I have separate videos about those. But the chiral center at carbon number 2 is the R stereocenter, and the alkene is a Z alkene. Once assigned, the stereochemistry information goes in a set of parentheses at the front of the molecule. We list all of the stereochemical information in numeric order based on the IUPAC numbering of the molecule, and we do not combine like stereochemical term. If there were 2 R stereocenters at carbons 2 and carbons 9, we would not say 2,9R. We would list them separately. 2R, 9R. So for this molecule, in numeric order, 2R, 4Z goes in front of the name of the molecule, separated from the rest of the name by a dash. And that gives us the full name for this molecule. 2R, 4Z, 5-ethyl, 2,6-dimethyl, hept 4-ene-al. You can really feel a sense of accomplishment when you can rattle off the entire name in order. The one thing I'm not going to do in this video is go through the nomenclature rules for benzene. Benzene is governed by a different set of IUPAC rules with its own set of subrules and sub-subrules, and I have a different video on the nomenclature of benzene rings that I'll link in the description below. That's the entire rule system for IUPAC nomenclature as you're likely to see it in this course. You are not expected to apply this rule system perfectly yet. Now you need to practice. Lots and lots of naming practice. If you'd like some of that practice, the next video in the sequence starts with the basic naming of alkanes, alkenes, and alkynes. Subsequent videos work through substituents, rings, and priority functional groups. Each video starts with a simple example and works towards progressively more complicated examples so you can see how those rules and subrules and sub-subrules activate in real molecules. That's where the understanding and the intuition is born. That's where this starts to click. I'll see you in the next video, ninjas.
Thanks for watching. The best way you can support this channel is to let your friends know about these videos, especially ones who go to different schools. Help spread the word around the country. As always, don't forget to like and subscribe.